Hello viewers, in this video I would like to discuss numerical integration. Numerical integration is the approximate computation of an integral using numerical techniques. Why do we use numerical integration or where we apply it? Numerical integration is applicable when functions do not possess closed form solutions or exact solutions. Here we have a function fx is equal to integral 0 to x e to the power minus t square dt. We get its solution in error function form. So here we can apply numerical integration to get an approximate solution of this. Second case is when data points are available in a tabular form. It means it is applicable when data for variable are available in the form of a table. Then we can find out the area under the curve. That is the integration. And the most straightforward numerical integration technique uses the Newton-Cotes formulas, also called quadrature formulas, which approximate a function tabulated at a sequence of equally spaced intervals by various degree polynomials. So here we see Newton-Cotes integration formula. We can see a curve here on xy axis, and this curve is denoted by fx. We take a point a is equal to x0 and function value at x0 is f0, function value at x1 is f1, function value at x2 is equal to f2, x2 is equal to x0 plus 2h, and last we have taken nth point b is equal to xn and function value is fn at this. So we have to find out the area under this curve, which is inside the points x is equal to x0 and x is equal to xn, denoted by a and b. To integrate a function fx over some interval ab, so ab are included, divide it into n equal parts such that fn is equal to fxn and h is equal to b minus a upon n. So this we have seen in this figure also, the 10 parts we have taken, and fn is equal to fxn, h is b minus a upon n, n is the number of parts. Then find polynomial which approximate the tabulated function and integrate them to approximate the area under the curve. Now we write I is equal to a to b fx dx, which is equal to x0 to x0 plus nh fx dx. We see that a is equal to x0 and b is equal to xn, which we have seen in previous slide, and xn is equal to x0 plus nh. Now we substitute x is equal to x0 plus ph, differentiate it, we get dx is equal to h dp. Now we put the value of x as x0 and x0 plus nh to get the limit values. So when we put x0, then we get p is equal to 0, and when we put x is equal to x0 plus nh, we get nh is equal to ph. It means p is equal to n. We substitute limits 0 to n and value of dx is h dp. We put x is equal to x0 plus ph, we get this I. To integrate it, first we expand fx0 plus ph with the help of Newton's forward interpolating formula, and then we integrate it term by term and substitute the limits. So we first integrate f0 p, and when we put the limits 0 to n, it becomes f0 n. Then we go to next p square by 2 del f0. When we put the limits, it becomes n square by 2 del f0, and so on. So this is our formula, that is Newton's Cotes quadrature formula. Hello viewers, in this video I would like to discuss trapezoidal rule for integration, and we have this figure in this slide where we can see there is a curve. At this curve we have taken 2 points and joined these 2 points with the help of a straight line. It means we are approximating the curve with the help of a straight line. So these 2 points on x-axis are a is equal to x0 and b is equal to x1, and function values are fa and fb at these 2 points respectively. It means we are approximating the function fx on x0 x1 by a straight line, and it is called trapezoidal rule. It is a 2-point formula, also we call it 2-point formula. Now we take Newton-Cotes quadrature formula, and in that we put n is equal to 1, and when we put n is equal to 1, we can write down I value as a to b fx dx, which is equal to x0 to x0 plus h, because only first point has been taken, fx dx. Now we will substitute value of x as we did in Newton-Cotes formula as x0 plus ph. We differentiate it and get dx is equal to h dp. We substitute value of x and dx in the value of I, and we write down the limits also as 0 to 1. So when we substitute f x0 plus ph and expand it with the help of Newton's forward interpolating formula, we get f0 plus p del f0, and limit is 0 to 1, h dp is value of dx. Now we integrate it term by term and substitute the limits. So we see it comes h f0 plus half del f0. Now we can expand del f0 and can write down as f1 minus f0, and we simplify the term which is in this bracket. We get h by 2 f0 plus f1. So I value we got h by 2 f0 plus f1. This is the trapezoidal rule, which is based on 2 points. The composite trapezoidal rule, here we have to evaluate a to b fx dx. So we subdivide the interval ab into n subintervals. In this figure we can see that fx is a function, and we have taken 2 points on this, which can be denoted by a and b on x-axis, and we have subdivided this interval a to b into n subintervals. So the area under the curve in each subinterval is approximated by a trapezoid. The integral is then approximated by the sum of all trapezoidal areas. So what we do, we take 2 points xi to xi plus 1 fx dx, and we use 2-point trapezoidal formula, which is h by 2 fi plus 1. Now we take all the trapezoids, so I takes value from 0 to n minus 1, and we take summation of all these. So this becomes summation I is equal to 0 to n minus 1 h by 2 fi plus 1. So now limit is here a to b fx dx. Now we open this summation, and we can write down h by 2 f0 plus f1, then next is f1 plus f2, next will be f2 plus f3, and so on till we reach to the last interval, and we get fn minus 1 plus fn. So we see first and last value has come once, and rest of the values, all other values have come twice. So we can write down h by 2 f0 plus 2 f1 plus 2 f2 up to plus 2 fn minus 1 plus fn. Now let's see one example based on trapezoidal rule. So this example is a river is 80 meters wide. The depth d in meters at a distance x meters from one bank is given by the following table. Calculate the area of cross section of the river. So x values are 0, 10, 20, 30, 40, 50, 60, 70 and 80, and depth d is 0, 4, 7, 9, 12, 15, 14, 8 and 3. These are corresponding values, means for x is equal to 10, depth is 4, and say x is equal to 60, depth is 14. Now we apply the trapezoidal rule, and we have to find out that what we need to calculate. So this is integral 0 to 80. These are the limits of x 0 to 80 fx dx. So what is fx dx? We don't know function here, so that is why we are applying this Newton Hello viewers, in this video I would like to discuss about Simpson's 1/3 rule for integration. Simpson's 1/3 rule approximates the function fx by a second order polynomial p2x, which passes through 3 sampling points. Earlier we have seen Newton's Cotes formula, and after that trapezoidal rule, where we have used 2 points, and in trapezoidal rule we approximate the curve with the help of a straight line. Here we are approximating the curve fx by a second order polynomial. So we can write down the integration I is equal to x0 to x2 fx dx. Here you can see that we are using 3 points x0, x1, x2, and we do as we did in Newton cotes or trapezoidal rule, and substitute x is equal to x0 plus ph, and then we take dx is equal to h dp, and we expand fx with the help of Newton's forward interpolating formula, and we get this expression. Now we integrate term by term, and after integrating term by term, so we have written here x is equal to x0 plus ph and dx is equal to h dp. Now we integrate and then we substitute the limits which have been changed to 0 to 2, and then we get the formula. So here we have integrated and limits are on right hand side 0 to, and when we have substituted we get this expression, which we can simplify after keeping value of del f0 and del square f0. So we have substituted. Now we collect the terms and we see this is the formula. So this is for first 3 points. We take next 3 points and then next 3 points, and then we can combine the formula. So in this case here we have taken only 3 points, and here error comes minus 1 upon 90 h to the power 5 f to the power 4 zeta, and zeta lies between x0 to x2. So this is our Simpson's 1/3 rule. As I said, we can take 3 points, then next 3 points, and then next 3 points, so we can get composite Simpson's 1/3 rule. And composites, to have a general formula, we can write down: to improve accuracy the integration interval is divided into n number of segments of equal width, where n is an even number. So what we do, h is equal to b minus a upon n. Now we write down this formula, that limits are a to b fx dx is equal to I is equal to 0 to n minus 2, n is an even number, h upon 3 fi plus 4 fi plus 1 plus fi plus 2. Now we can expand it and see this is the formula: h by 3 f0 plus 4 f1 plus f2 plus f2 plus 4 f3 plus f4. So you can see first 3 points give you f0 plus 4 f1 plus f2, next 3 f2 plus 4 f3 plus f4, and so on. Last 3 points are fn minus 2 plus 4 fn minus 1 plus f1. So we have combined them, and now we can have composite formula. So we have collected first and last term f0 plus fn, then odd terms, and each odd term is multiplied by 4, so 4 common, f1 plus f3 plus fn minus 1, then even terms, twice of even terms, so first term plus last term plus 4 of odd terms plus twice of even terms. H by 3 is outside. Then we can have global error, and global error is b minus a upon 180 s to the power 4 f to the power 4 zeta, which is order of 4. Let's have one example. Here example is: evaluate the integral 0 to pi by 2 under root sin x dx for n is equal to 6 using Simpson's 1/3 rule. It means n takes value 0, 1, 2, 3, 4, 6, 7 points are there, and h is equal to b minus a by n. It means which is equal to pi by 2 minus 0 by 6 is equal to pi by 12. So we find out the points, that is values of x, which is 0, pi by 12, pi by 6, pi by 4, pi by 3, 5 pi by 12 and pi by 2. When we substitute these values of x in sin x, we get the value of under root sin x here, and which have been calculated with the help of calculator. So we substitute the values of function in the composite Simpson's 1/3 rule. Here we see the formula is integral a to b fx dx is equal to h by 3 f0 plus fn, first and last value, plus 4 of odd values plus twice of even values. So here f0 is 0, f1 is 0.5087, f2 is 0.7071, f3 is 0.8409, f4 is 0.9306, f5 is 0.9828 and f6 is 1. So we substitute f0 is 0 plus f6 is 1 here, and similarly we keep all the values here and find out the value of integral 0 to pi by 2 under root sin x dx, which is equal to 1.1872. Now Simpson's 3 by 8 rule. Simpson's 3 by 8 rule approximates the function fx by a third order polynomial p3x, which passes through 4 sampling points. So 4 sampling points will be x0, x1, x2, x3. So our integral is x0 to x3 fx dx, and we expand fx with the help of Newton's forward interpolating formula, as we did in rest of the methods, trapezoidal and Simpson's 1 by 3 rule, as well as in Newton's COTES formulas. So we get this h integral 0 to 3 f0 plus p del f0 plus p into p minus 1 upon factorial 2 del square f0 plus p into p minus 1 into p minus 2 upon factorial 3 del cube f0 dp. Now we integrate term by term and substitute the limits. So we get this, and we have expanded del square f0 del cube f0 as well as del f0, and then we see this is the formula we get for 4 points. So here error is minus 3 upon 80 h to the power 5 f to the power 4 zeta. To improve accuracy, divide the interval of integration into n segments where n must be multiple of 3. So here we can write down the composite formula also. A to b fx dx is equal to 3h by 8 f0 plus fn plus 3 into f1 plus f2 plus f4 plus f5 plus fn minus 1 plus twice of f3 plus f6 plus fn minus 3. And here error is minus b minus a upon 80 h to the power 4 f to the power 4 zeta. Now let's see one example. The length of an ellipse x is equal to a cos t, y is equal to b sin t. T lies between 0 and 2 pi is given by L is equal to 4a integral 0 to pi by 2 1 minus e square cos square t to the power half dt, where b square is equal to a square 1 minus e square. Find L when a is equal to 2 and b is equal to 1 by Simpson's rule with h is equal to pi by 6. So b square is equal to a square 1 minus e square. We put values of b and a, and we get e square is equal to 3 by 4. So L is equal to 8 0 to pi by 2 1 minus 3 by 4 cos square t to the power half dt. We say it is equal to 8i. So this whole integral is equal to I, and the term 1 minus 3 by 4 cos square t to the power half is equal to f. So we say t is taking value 0, pi by 6 is the value of h, so 0 pi by 6 to pi by 6 is pi by 3 and pi by 2. Now we calculate values of f at each value of t, and we substitute here in this tabular form. Now we calculate I, that is by using Simpson's 3 by 8 formula. We put 3h by 8 f0 plus 3f1 plus 3f2 plus f3, and we substitute these values here. We get value of I as 1.215. Now our integral was 8 into I, so we multiply it by 8 and get the values 9.7207. Thank you.